Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will continue talking about the modulus of a complex number. Well, M, A, and B are 3 points with affixes Z, M, Z, A, and Z, B. We saw first that the modulus of Zm is the distance from O to M. We know also that the modulus of Zb minus Za is the modulus of Z of vector AB, which is the distance between A and B. So in case we just have one letter, the modulus would be interpreted as OM, and in case we have two letters, as we see here, the modulus will be interpreted as the distance from A to B or the distance from B to A. Well, what do we have here? In fact, we have here the ratio of AB over CD, and if we apply the properties of moduli, we're going to get this result. Let's see this example. We have A, B, and C are 3 points with affixes as you see here. The question is to prove that the triangle ABC is equilateral. Well, to have an equilateral triangle, we must have 3 equal sides. I'm going to begin with AB. If I apply this property, AB is the modulus of ZB minus ZA. If we replace ZB and ZA, we get this quantity, which is the modulus of 4, which is 4. Well, if we continue similarly, what is AC? It's the modulus of ZC minus ZA. By replacement, we get this answer, and the modulus of this quantity applying the square root of a squared plus b squared would also be 4. So till now I know that AB is equal to AC. And if we find BC, this is the modulus of ZC minus ZB. It will be the modulus of this quantity, which is also 4. So by now I know that AB is equal to AC is equal to BC, so the triangle is equilateral. Let's see this application. A, B, C, and D are 4 points having such affixes. The first part asks to prove that ABCD is inscribed in the circle C with center L 0 and radius 1. Try to do it alone. In other words, you need here to prove that LA is equal to LB is equal to LC is equal to LD, and all of these distances should be equal to the radius 1. Let's begin. If we find the affix of point L, we get ZL is equal to 2. So LA is the modulus of ZA minus ZL, which is 1. LB is the modulus of ZB minus ZL, which is also 1. LC is equal to 1 and LD is equal to 1 by simple calculations. So we can say that LA equals LB equals LC equals LD equals 1. So all of these points belong to the same circle, and we can state that ABCD is inscribed in that circle. While E is a point with affix the square root of 2 over 2 plus 2 plus the square root of 2 over 2i, and the question is to verify that E is on this circle. Well, how do we verify that E belongs to the circle? Try to do it alone. In fact, E belongs to the circle if the distance from L to E is equal to the radius. So LE is the modulus of ZE minus ZL, which is the modulus of this quantity, which is 1. So we can say that E belongs to the circle. Let's see the question. We have MA and B are 3 points with such affixes. You see ZA is negative 2, ZB is 2 plus I, so A and B in this case are fixed points, whereas M is a point with affix Z, so M is a variable point. The question is to find the set of points M in each of the cases below, if the modulus is 2. Well, if we just apply what we saw at the beginning of this video, the modulus of Z is 2, so the modulus of Zm is 2, so OM is 2, and if OM is 2, this means that M moves on the circle with center O and radius 2. This is the same as the second case here. Let's see the second question. This modulus is equal to that one. If we just replace, we get this quantity. Remember, we must always have z minus z of a certain point. So we get zm minus za is equal to zm minus zb. If we replace negative 2 by za and replace 2 plus I by zb from the beginning. So from here we can say that AM is equal to BM. So M moves on the perpendicular bisector of segment AB. Now let's see the third case. If we apply the same procedure as part B, this is what we have. If we take a minus in common in the numerator and another minus in the denominator, in fact we get 2 plus I, and 2 plus I is nothing but ZB, and we get minus I, and we don't have any minus I here, but this is a fixed point, so we define it. We come and state that ZG is minus I to replace it here. And if we go back, we get the modulus of Zm minus Zb over Zm minus Zg, which is equal to the modulus of I, which is 1. So in this case, we get Mb over Mg is 1, or Mb is equal to Mg. So M moves on the perpendicular bisector of Bg. Remember here that B and G are two fixed points. Well, let's see this application. We have M prime, E, and F are 4 points. M and M prime are 2 variable points, whereas E and F are 2 fixed points, and we have this relation between Z and Z prime. The first part asks to write the modulus of Z prime in terms of OM prime. Try to do it alone. This is very easy. Well, the modulus of Z prime, if we replace Z prime by Z of M prime from here, from the statement of the problem, we can see that the modulus of Z prime is the distance from O to M prime. The second part asks to write the modulus of this ratio in terms of ME and MF. Try also to do it alone, and this is also very easy. Well, the modulus of this ratio, if we replace Z by Zm and I by Ze and minus I by Zf, this is what we get, and applying the property, this is nothing but Me over Mf. Finally, the question asks to find the set of points M when M prime moves on the circle with center O and radius 1. Try also to translate this statement into a mathematical expression and then find the set of points. Well, if we want to translate this statement, what do we mean by M prime moves on the circle with center O and radius 1? This means that OM prime is 1 and OM prime is nothing but the modulus of Z prime. So we can tell from here that the modulus of Z prime is 1. But if we go back to this relation and we apply a modulus here and a modulus there, this is what we get. By replacement, we get 1 equals ME over MF, or ME is equal to MF, or M moves on the perpendicular bisector of segment EF. Now Rami or Amir, M is a point with affix Z, so M is a variable point. We need to find the set of points M when the modulus of this quantity is equal to 5. When Rami defined a point A such that ZA is 1 minus I, and then he wrote the modulus, he took a minus in common, he got the modulus of Zm minus Za is 5, so M moves on the circle with center 1 minus 1 and radius 5. Amir replaced Z by x plus Iy because he couldn't tell what to do. Let's see. So if we just replace Z by x plus I, this is what we get. Now, collecting the real part alone, the pure imaginary part alone, and if we square both sides, this is what we get. And in fact, Amir squared both sides in order to get rid of the square root sign. So here we get x minus 1 squared plus y plus 1 squared is 25. So M moves on the circle with the center 1, negative 1, and radius 5. I think both Rami and Amir did it well. They did it in a correct way, but each one of them used a different strategy.